Hi, welcome to my video. In this video, I am going to explain about vector subspaces. In my previous video, I have defined vector space and I have proved the examples for vector spaces also. To know all this, you can check the links in my descriptions. So now the definition goes as such: let V be a vector space over the field F and W is contained in V. Then W is called a subspace of V if W itself is a vector space over the field F with respect to the operations of vector addition and scalar multiplication in V. That means V is given as a vector space over the field F and W is going to be the subset of V. When W will be the subspace of V means W itself must be a vector space over F, then it is going to be the subspace for the vector space V. For example, the set V of all ordered triplets A1, A2, A3 over the field of real number is a vector space with respect to addition and scalar multiplication. The set W of all ordered triplets form A1, A2, 0 is going to be the subset of V, and this is also a subspace of V because it obeys all the axioms of a vector space and it is a subset of V, and hence it's going to be the subspace. So now criterion for a subset to be a subspace. Apart from this, let us see what are the other criteria for a subset to be a subspace. So the first theorem says as such: a non-empty subset W of a vector space V is a subspace of V if and only if for alpha beta in W, alpha plus beta must be in W. For any A in F, alpha in W, A alpha must be in W. That means A is a scalar which belongs to F. And the same theorem can be rewritten as: the necessary and sufficient condition for a non-empty subset W of a vector space V of F to be a subspace of V is that W must be closed under vector addition and scalar multiplication in V. So the same theorem can be written in these two forms. The proofs are going to be the same. So here let us check the theorem. The statement of the theorem is being given: non-empty subset W of a vector space V is a subspace. So when W is going to be the subspace means when these two conditions are satisfied, and vice versa, if these two conditions are satisfied, then W can be the subspace for the given vector space. So we'll prove the necessary and sufficient conditions. So for the necessary part, we'll assume the first part and prove the second one. And conversely, we assume the second part and prove the first one. So for necessary part, I am assuming that suppose W is a subspace of V, then W itself is a vector space according to the definition of the subspace over F under the same operation of addition and scalar multiplication as defined in V. Since it's going to be the vector space, obviously it must be closed with respect to vector addition and scalar multiplication. So easily it is being, by the definition itself, we can prove that alpha beta in W implies alpha plus beta is also W. So we're closed under vector addition and closed under scalar multiplication. Now for the converse part, let us take these two conditions are true and we have to prove that W is going to be the subspace of V. So here, suppose that W is a non-empty set of V. So obviously it must be a non-empty subset of V, and then W is closed under vector addition and scalar multiplication by assuming these two conditions. Now we have to prove that W is going to be the subspace, vector space of V. So here let alpha belongs to W and 1 is the unit element of F, then minus 1 also belongs to F. Because 1 is a scalar and minus 1 also is scalar, F is a field. Now W is closed under scalar multiplication in V. Then minus 1 in F, alpha belongs to W implies minus alpha belongs to W according to the second condition. Instead of A, we have taken minus 1 because it is in F, alpha in W. So A into alpha belongs to W. So minus 1 into alpha minus alpha belongs to W. Thus, the additive inverse of each element of W is also in W, because alpha in W means we have proved minus alpha is in W. So from that we arrive the conclusion that the additive inverse of each element of W is also in W. So W is closed under vector addition because this according to the first condition. Therefore, alpha in W minus alpha in W. So alpha plus minus alpha will give you 0, which belongs to W. where 0 is the 0 vector in V. So hence the 0 vector of V is also the 0 vector of W. Since the elements of W are the elements of V, therefore vector addition is commutative as well as associative in W. Hence, W is an abelian group with respect to vector addition. Also, it is closed under scalar multiplication according to our assumptions. So here, how do we say it is going to be a commutative or abelian group? Means it has an inverse, it has an identity element as a 0, and already closed under vector addition, scalar multiplication. It is commutative, associative, everything is satisfied, and hence is an abelian group. Actually, it is just a non-empty subset of V. Now I am able to prove that it is a group with respect to vector addition. It's also closed because of the second condition, and hence the remaining axioms of vector space will hold in W since they hold in V, because the elements are coming from V. What are the subset mean? The elements should be present in the primary subset. From that only we are taking the elements. So obviously it contains all the properties of vector space. Hence W itself is a vector space for these two compositions. Hence W is a subspace of V. Thanks for watching. See you in the next video.